Okay, so in our first video, we're going to talk about limits, and we'll start with a little bit of review because we've done limits already. So what we're doing is graphically, and there's a way we can do it with the numbers in the table, but first, graphically, we're going to look at our x values as they approach the indicated value. So whatever it says x is approaching, you want to look towards that and then see what the y value is approaching. That's our informal definition of a limit. Okay, so that's one way to look at it. You could also think about as numbers, the x values are getting closer and closer. So fill in numbers into the function or into the expression and see what values it's getting closer and closer to. Okay, so let's review. We first did this with infinity and negative infinity. So example 1, the limit as x approaches infinity. So as the x values are getting bigger and bigger. So on the graph, that means as x's are going to the right forever and ever, this is asking us what is our y value getting closer to. So I had already graphed this one. So what are our y values getting closer and closer to? They're getting closer and closer to infinity. You could also plug in x values that are getting closer and closer to infinity. So that means they're getting bigger and bigger. So if you were to, and you can see my table, plug in 4 squared is 16 plus 3 is 19. As it gets closer, if it's 7, you plug that in, it's 52. If you plug in 100, right, you're going to get bigger and bigger and bigger. Plug in 1,000, so it's getting closer and closer to infinity. All right, so let's look at example 2. So in this function, so I graphed it 1 over n, and n is getting closer to infinity. So again, n is going to the right forever and ever, and we want to know what the y values are doing. So if you notice the y values, so I can even try to trace this. So the y values, it looks like they're going down and down and down, but they're not going down to negative infinity. They're getting closer and closer to 0. And in the table, this one's harder to see. Here, so I'm getting my x values are getting closer and closer to infinity, and my y values look like they're getting smaller and smaller and smaller, but I maybe can't tell, so you'd have to scroll in your table to see that they're getting closer and closer to 0. So then we did limits where we were focusing on a specific number, and if we were saying that our n or x value, whatever, was approaching a number, we had to say if it was approaching from the right or the left. So notice in example 3, I'm saying n is approaching 0 with a little plus sign. So that means from the right. Okay, so we're going to approach 0 from the right side. So that means we're going to go this way, but we're not going to go forever. We're just going to go towards 0 from the right. So I can trace this. So my y values looks like they're going up and up and up and up and up forever and ever to infinity. And then for example 4, I have the exact same function, but this time we have the negative. So this time we are approaching from the left side, so we're going to approach 0 again, but from this side. So looks like our function's decreasing forever and ever and ever and ever, so we're going to negative infinity. Now what's new is that we're now looking at as n approaches 0, but notice I don't have a plus or a minus sign, so that means I'm coming from both directions. Well, when we're coming from this way, it's approaching infinity from the right, and when we're approaching from the left, our limit was negative infinity. Well, when I don't have the plus or minus, then I'm approaching from both sides, and if they aren't approaching the same value, then our limit doesn't exist. So we say the limit doesn't exist, or DNE. I just like to write that as an abbreviation, so I don't always have to write the limit does not exist. If you ever saw the movie Mean Girls, right, then you're saying that over and over again. That was in that movie. Okay, so that's what we're looking at. Now in example 6 down here, I have the limit as x approaches 3 of 2x minus 1. So I graphed 2x minus 1, I looked at the table, so I'm approaching 3. Notice I have no little plus or minus sign, so I have to go from the same way. So if I'm going towards 3, so from the left and the right, so let's see, 1, 2, 3, so it's like up here somewhere. So as I come from the left side, it's going down towards the y value there looks like 5, and if I were to come from the left side, it's also approaching 5. So it's approaching the same value. So the limit as x approaches 3 of 2x minus 5 equals 5. All right, so now let's kind of talk about doing this, and we can really do these without always having to graph them. There is algebraic ways to do this, but first off, if a function is continuous, right, that will be helpful on how we find our limit. So we knew if a function was continuous, you can draw it or trace it without lifting your pencil. That really wasn't a definition, that was just more of a geometric description or graphic description. What the actual definition is that a function is continuous at a, so we're not talking about the whole function, but at specific a values, if the limit as x approaches that value of the function equals f of that value. So basically substituting in the function the value you get. So that's our definition. So if a function is continuous at a, then to find the limit at a, then you just have to plug it in. Okay, and that's what we call direct substitution. Okay, so let's try direct substitution. Find the limit using direct substitution. Well, 2x minus 1 is a continuous function. I drew it up here. Okay, that's 2x minus 1. That's continuous at 3. Okay, it's continuous there. So since it's continuous, then all I have to do is plug in 3. So notice my answer is still 5. So I knew that was my answer before by looking at the graph. So I still know by plugging it in that my answer is still 5. Okay, so the next one, the limit as x approaches 3 of x squared minus 2. So x squared minus 2 is a quadratic. That is continuous. It's just a parabola. So all we have to do is use direct substitution. So 3 squared minus 2. So that answer is 7, right? 3 squared is 9 minus 2 is 7. So that's the limit as x approaches 3 of x squared minus 2. So if a function is discontinuous at a, so at a it's not continuous anymore, then we probably won't we won't be able to use direct substitution, but we can still find it algebraically by simplifying first to take care of it. So let's look at our example. So to find the limit algebraically, for this problem. So our function is x squared minus 9 over x minus 3. We're going to find the limit as x approaches 3 of our function. I'm just going to rewrite it. Now I'm looking at this and I know that there must be some problem in x minus 3, whether it's an asymptote or a whole, whatever it is, right? If I were to plug in 3 in the denominator, I get 0, and I can't do that. So what I do is first I simplify. So I notice that the top factors, and then I notice that it will cancel with the denominator, and so the limit as x approaches 3 of x plus 3, now I can substitute in 3, and I get that the limit is 6. And you can, if you like, get your calculator out, graph x squared minus 9 over x minus 3, and you'd actually notice that there's a hole where x is 3, but from the left and the right as you're approaching 3, it is approaching the value of 6. It's not defined there, but that's its limit. It's approaching that value. Okay, so there are lots of properties of limits. They're on page 775 in your book. If you'd like to look through it, go ahead. We are not going to be doing these, but if you wanted to look, go ahead. There's also an example, similar, or actually this example is in your book on that same page if you wanted to go through it. Okay, so so when we're asked to find a limit, the first thing you want to do is just try to plug in the value, right? If it's continuous, plug it in. Now, if that doesn't work, if it's not continuous at that value, then make sure you try to simplify first, maybe factor and cancel like we did. And once that happens, and once the undefined place is gone, go ahead and plug in your value. But sometimes you can't simplify at all. So you can't substitute it in, it's undefined. Sometimes you can't simplify it. So our third option is to graph it, look at the table, plug in numbers, try to see what the limit is. So you're approaching the x value, what is the y value approaching? Don't forget to look from the left side and the right side. It must be the same for that to be the limit. Otherwise, the limit doesn't exist. All right, now sometimes you're going to have piecewise functions. So I have my piecewise function is defined as x plus 4 if x is greater than or equal to 2, and 3x if x is less than 2. Now, to save some time, I graphed x plus 4 here, but I have all of x plus 4. So let's see if I can correct it a little bit. So my x plus 4 is only for the x is greater than or equal to 2. So I'm going to find the x value of 2, which is right here, and it's going to be a closed circle at 2. That's close enough. And it's over here. So this is the part I'm looking at. So I'm not looking at the blue. So now I need to draw y equals 3x for x is less than 2. So at 2, let's see, my value is 6, so 1, 2, 3, 4, 5, 6, okay, here, which is already a point, and then at 1, it is 3, 0, I'm getting as close as I can, -3, okay, so it looks like this. All right, so the green is my, we'll just ignore all this, don't look at that. All right, so the green is my piecewise function. All right, so I'm looking for the limit as x approaches 2 of my function. So I need to look, okay, so I need to look at going to the 2 from the left and the right. So from the right side, so if I'm approaching from the right side, it looks like my value is approaching 6. I could use my table, I could kind of plug it in, I could just use my graph here. So I'm approaching 6 this way, and as I'm approaching from the left side, so as I'm going from the left side, my graph's going up and it's also going towards 6. Okay, so that's my limit on this one. All right, so I have down here, I'll use red this time. All right, I have the same function except I have x plus 4 if x is greater than or equal to 0. So this time my x plus 4 greater than or equal to 0. Okay, so where's 0 on this function's here, closed circle, and I'm going greater than 0 is to the right. Okay, so we're looking at the red, ignore this. All right, so for y equals 3x, if x is less than 0, well at 0, 3 times 0 is 0, but it's an open circle. And then put in -1, that's -3, so I'm down here. So that's what my graph's going to look like there. All right, so there's my piecewise function. So this time, the limit as x approaches 0. So from the right side, if I go from the right side, I look like my y values are approaching 4. Okay, so I'm approaching 4 on that side. And from the left, if I go towards 0, I'm approaching 0. Since those don't match, since we're not approaching the same number, then our limit doesn't exist for this one. Okay, so just lastly, sometimes if you notice the limit we were looking for was always where the split was in the function, that's not always going to be true. So let's say I look at this last example here, I look at the same problem, but this time I'm going to approach, x is going to approach -2. All right, well, if I'm approaching -2, so -2, that's going to be right in here. All right, so from the left side, I am approaching -6, and from the right side, I'm also approaching -6. So this one would be -6. So it's not always at the split, so just please be careful of what x is approaching.